Okay, our last test for positive series, this one's called the limit comparison test. The last one was a direct comparison. This one is the limit comparison test. So we're still working with positive term series. That means that a sub n and b sub n are both greater than 0, no negative terms. If the limit of the ratio of those two series equals some positive finite number, that means these two series are growing at the same rate. And they only differ by some constant. So that means overall their growth is similar. If one of them is approaching the x-axis fast enough, the other one will approach the x-axis fast enough also. They only differ by some simple multiple called L. So if a sub n and b sub n will both converge or diverge in that situation. So let's go back to the example we ended the last video with. That's the 1 over 3 to the n minus 1. We're still going to use everything that we did before. We still know that this is a positive series. We are still going to compare this to 1 over 3 to the n. And we still know that this 1 over 3 to the n converges because of the geometric series test. Now we're going to compare these two to see if they grow at the same rate. So let's use the limit comparison test. We're going to find the limit as n approaches infinity of one over the other. It doesn't matter which one is in the top of the fraction or the bottom. It doesn't matter. We just need to make sure that they're growing at the same rate. So I'm going to test this with 1 over 3 to the n minus 1 over 1 to the 3n. So that's the limit comparison test. If we get a constant value or a positive number out of this, then we know that these two are growing at the same rate. So let's do a little bit of math here. I'm going to divide that bottom fraction by flipping and multiplying it. If I multiply those two fractions together, I get 3 to the n over 3 to the n minus 1. As n approaches infinity, this minus 1 does not affect the overall growth of these two exponential functions. So really what I'm comparing is 3 to the n over 3 to the n. They're growing at the exact same rate. So that means since 1 over 3 to the n approaches the x-axis fast enough, then so does 1 over to 3n minus 1. Okay, so we knew that 1 over 3 to the n converged. Therefore, we know that n equals 1 to infinity of 1 over 3 to the n minus 1 converges by the limit comparison test. Okay, let's do one more. Looking in this one, I'm just going to use the limit comparison test. Let's talk about positivity first. I know that if I plug 2 in, 2 squared is 4, 4 minus 1 is a positive number, 2 cubed is also positive, and anything greater than 2 plugged in will result in the same thing. So this is definitely a positive series. Now finding something to compare this to, think about this again. Remember, we're trying to find a function that grows at the same rate. So if I'm trying to find something that grows at the same rate, I'm looking at what does this series approach as n approaches infinity. So if I look at this and as n approaches infinity, I know that minus 1 is inconsequential, and n squared over n cubed reduces to 1 over n. So I'm going to say that this compares to 1 over n. I don't have to determine which one's greater or which one's smaller. It doesn't matter in this case. We're not looking at a direct comparison. We're looking at a limit comparison. We know a lot about 1 over n, and we know that from 2 to infinity, 1 over n is going to diverge to harmonic series, or the p-series test. Okay, so let's look at the limit. Let's compare these as n approaches infinity. I'm going to do one over the other. It doesn't matter which one's which, so I'll do it the other way around this time. I'm going to flip and multiply. So I've got 1 over n times n cubed over n squared minus 1. If I multiply those together, 1 times n cubed, n times n squared minus n. As n approaches infinity, this minus n becomes inconsequential. So really what I'm comparing is the growth of n cubed over n cubed, which is 1. This is a positive and finite value. Since we know that 1 over n that we were comparing it to diverges, that means our series also diverges. N equals 2 to infinity of n squared minus 1 over n cubed diverges by the limit comparison test. Okay, that's it for our positive sine series. We've only got one unit left, and that's varying sine series, so that's